Arnold L. Rosenberg. Abstract: the advantages of three-dimensional rcmts are studied by comparing sample three-dimensional reahzaons of certain common families of rcmts, namely permutation networks, FFT circmts, and complete binary trees with the FAMDS optional two-dtmens onal reahzatlons. These circuits are then used as building blocks to obtain efficient three-dimensional realizations of arbitrary circuits. The results obtained indicate, roughly, that bounds on area, both upper and lower, in the neighborhood of order n2m, the two-dtmens onal case, translate to bounds on volume m, the neighborhood of order na/2m, the three-dimensional case. Moreover, several of the upper bounds are attainable using idealized realizations that have actwe devices on only one level and that use the third dimension only for wire routing. Such reahzaons place fewer demands on the fabrication technology. However, it is also shown that unrestricted use of the third dimension can yield reahzaons that are more conservative of volume by the factor log/2n than any one actwe level reahzaon can be. Finally, examples are presented where two-dimensional reahzaons reduce wire lengths as large as n/ln. Wide equivalent three-dimensional onal reahzatlons can get by WTH wire lengths not exceeding n/2. Thus, at least in the worst case, there are substantive savings from three-dimensional onal circuit realizations in both material area versus volume and tune wire length. Categories and subject descriptors B.2 arithmetic and logic structures miscellaneous. B.71 integrated circuits types and design styles. VLSI F2.2 analysis of algorithms and problem complexity. Non-numerical algorithms and problems routing and layout. General terms design theory adminal keywords and phrases three-dimensional onal CMT reahzaons graph embeddings permuta un networks FFTC cults. 1. Introduction. One would anticipate three benefits if microelectronic circuits could be realized in a three-dimensional medium. First, one would expect wire routing to become easier and more systematic. Next, since one could avoid obstacles by using the third dimension, one would expect runs of wire to be shorter, at least in the worst case. These expectations have been realized in the modestly three-dimensional circuit packages reported by IBM 18 and by Hughes Research Laboratories 3 to 6. Finally, since avoiding obstacles in a two-dimensional environment can require circuitous routing of wires, and since such routing consumes much area, one would expect a savings in material, that is, the volume of a three-dimensional realization of a circuit might be less than the area of any two-dimensional realization. But it is not clear. Part of the research reported here was done while the author was with the IBM Thomas J. Watson Research Center, Yorktown Heights, New York. And part of T was supported by the National Science Foundation under Grant MCS 81 to 16,522 authors addressed Department of Computer Science, Duke University, Durham, North Carolina, 27706. Permission to copy without fee all or part of THS material S granted provided that the copies are not made or distributed for direct commercial advantage. The ACM copyright notice and the title of the publication and its date appear. And notice is given that copying is by permission of the Association for Computing Machinery. To copy otherwise or to republish requires a fee and/or specific permission. Copyright 1983 ACM 0004-5411/83/0700-039$70075. Journal of the Association for Computing Machinery, Volume 30. Number 3. July 1983. pp 397 to 416. 398. Arnold L. Rosenberg. How great these savings are likely to be. It is the purpose of this paper to demonstrate by an abstractee study that at least the last two expectations are well-founded and can manifest themselves in unbounded savings in both wire length and material. Since we have done only a case study, we cannot comment about the first expected benefit. We have intentionally been vague to this point concerning the level of circuit implementation at which we are proposing the use of a three-dimensional medium. The abstract setting of our case study does not distinguish between the problem of laying out gates and their interconnections on or in a chip and the problem of laying out chips and their interconnections on or in a printed circuit board. Thus, the patient reader can view our study as predicting the kind of gains in efficiency that will be achievable when the current technological obstacles to the fabrication of truly three-dimensional chips are overcome. The less patient reader can view it as an indication of the currently achievable benefits of three-dimensional circuit boards, although we obviously want to stress the potential benefits of three-dimensional circuit realizations. We should also mention some of the problems inherent in the task of implementing such realizations. This fist of problems should be viewed in perspective. The problems in the list did not stop the president of Texas Instruments, quoted in 7, from predicting the feasibility of such chips within the decade. Most of these problems accompany the proposal to make three-dimensional chips, the problems with circuit boards being minor in comparison. However, one problem exists also with circuit boards, though far less than with chips, namely, the problem of registration. In the miniature world being discussed, it is not a triviality to ensure that corresponding positions on successive layers of either a chip or a stack of circuit boards line up. In fact, with the current technology for fabricating chips, as described, say, in 14, even the target of 2 or 3 more metal layers for wire routing would pose non-trivial problems. A related second issue that plagues the chip fabrication process is the difficulty of creating true cylindrical holes. Current fabrication processes are plagued by holes that have accentuated tops and/or bottoms, see, e.g., 14. Sector 4.7, Figure 4.26, because of effects like diffraction, scattering, and non-uniform exposure to solvents, and these effects increase with the depth of the hole. It is worth noting, however, that recent work on X-ray beam and refined optical lithography suggests that both of the preceding problems will be less critical in the future than they are now. A third major issue in the fabrication of three-dimensional chips is the problem of cooling. Even with current three-layer chips, one must pay careful attention to power consumption and concomitant heat generation. A solid three-dimensional chip would present formidable problems in this regard. This problem may disappear if a radically different technology becomes dominant and would diminish in severity if three-dimensional chips prove to require much smaller linear dimensions than their two-dimensional counterparts. However, even with current technology, one avenue for possibly ameliorating this problem would be to design three-dimensional chips that have active devices, transistors, gates, etc., on only one level, either the bottom or the top, and that use the third dimension only for wire routing, since wires give off less heat than active devices. Our formal framework can model this restriction, and we show that the dramatic savings in both material and wire length are often attainable even in its presence. Warning: we shall present examples wherein these dramatic savings are not attainable with one-active level realizations, and other examples where dramatic savings are attainable, but not to the extent achievable with unrestricted three-dimensional realizations. The fourth problem we mention is one that would be encountered if one tried to build unrestricted three-dimensional chips using MOS technology. Active devices in this technology are built upon a 399 substrate of monocrystalline silicon. Placing active devices deep inside a three-dimensional chip would require one to deposit multiple layers of this form of silicon, and subsequent processing of the chip could easily cause its delicate crystal structure to break up into the electrically dissimilar polycrystalline form of silicon. BDDT recent work on devices at Texas Instruments 9 IBM 27, and Lincoln Labs 21, suggests that full layers of monocrystalline silicon are not needed. Acceptable transistors can be fabricated on islands of monocrystalline silicon that sit on a sea of oxide. Moreover, this problem, as well as the earlier one, would be ameliorated by restricting attention to one-active level three-dimensional realizations. In what follows, we shall consider both the unrestricted and one-active level cases, the former being meaningful for circuit boards and perhaps for future chips, and the latter being meaningful perhaps for even nearer future chips. The vehicle for our case study is the family of rearrangeable permutation networks. 2. Because of similarity in structure, we might just as well have used circuits for implementing the FFT as our vehicle. Our notion of the realization of a circuit follows the approach of 10 to 12, 16, 17, 19, 22, 24, 26. We view circuits as graphs whose vertices correspond to the active devices, transistors, gates, etc. in the chip model and chips in the circuit board model of the circuit, and whose edges correspond to the wires connecting these devices. We view the medium in which the circuits are to be realized as grids, two-dimensional in the cited sources, possibly three-dimensional here. The process of realization consists of an embedding of the circuit graph in the grid. The material used in an embedding is just the area, in the two-dimensional case, or the volume, in the three-dimensional case, of the smallest rectangular grid capable of holding the circuit graph. We assume throughout that A. Unit length of wire has unit area in the two-dimensional case and all unit area cross sections in the three-dimensional case. The rationale behind the unit height assumption in 3 dimensions is to use the space to diminish the coupling effects that could plague closely overlapping runs of wire. The main results of our case study can be summarized as follows. 1. There is a three-dimensional realization of the n-input rearrangeable permutation network that consumes volume 0, n3/2, and there is a one-active level 3-dimensional realization of the network that consumes volume 0, na/210gn. The unrestricted realization is within a constant factor of being optimal, and the one-active level realization is within a factor of log/2n of being optimal. This contrasts sharply with the fact that any two-dimensional realization of the network consumes area Fn2. 2. These material-saving unrestricted and one-active level three-dimensional realizations of the n-input rearrangeable permutation network have maximum wire length O(n/2). This contrasts with the fact that any two-dimensional realization of the network has maximum wire length F(n/log(n). 3. There is an unrestricted three-dimensional realization of the depth-lon complete binary tree with maximum wire length O(n/3). This contrasts with the fact that any two-dimensional or one-active level three-dimensional realization of the tree has maximum wire length F(nl/2/lon). 4. Our material and wire-saving three-dimensional realizations of n-input permutation networks can be used to devise efficient three-dimensional realizations of every small degree and vertex graph, specifically realizations with volume O(n/2) and wire length O(n1/2). This contrasts with the fact that there exist small degree and vertex. Note it when for real-valued functions f and g, we Cf equals OG, or, equivalently, GF, if and only FF there is a constant C greater than 0 such that Fx _CG x for all sufficiently large x. For 100. ARNOLD L. Rosenberg. Graphs all of whose two-dimensional realizations consume area Fn2 and maximum wire length Fn/log(n). We turn now to the task of establishing our formal framework and proving these and related results. 2.1 Graphs, permuters, and grids. A graph G comprises a set V of vertices and a set E of doubleton subsets of V called edges. An edge, U, V of G is said to be incident to vertices U and V. The degree of a vertex V of G is the number of edges incident to V, and the max degree of G is the largest degree of any of G's vertices. A path in the graph G equals V, E is a finite sequence of vertices of the form VL, V2, Vn, where each set V plus X is an edge of G. We shall term a set of paths in a graph independent if no two paths share an edge. The diameter of the graph G is the maximum distance between any two vertices of G, where the distance between two vertices is the length of the shortest path connecting them. We now present certain families of graphs that are of special concern to us here. An n-permuter is a graph with two disjoint designated n-element sets of vertices, termed the inputs and the outputs of the graph, with the following property. Given any one-to-one association between the inputs and the outputs, there is a set of n independent paths in the graph that realizes the association. Of particular interest for our upper bounds is the family of vertex minimal, in order of growth, among bounded fan-out permuters, and permuters due to Bell's, too. For NA power of 2, the n-rearrangeable network Rn is defined recursively as follows. R2 is the complete bipartite graph on two input vertices, inputs 1, 2, and 2, 2, and 2 output vertices. Outputs 1, 2, and 2, 2. Rn is obtained by taking A n input vertices, inputs 1, n, 2, n, n, B n output vertices, outputs 1, n, 2, n, and C 2 copies of Rn/2. For Ken/2 E inputs, K, n, and K plus n/2, n are connected by edges to inputs, K, n/2, of each copy of Rn/2, thus forming a copy of R2. Outputs are connected in an analogous fashion. See Figure 1. The graph Rn is leveled in a natural way. One starts with the level n inputs, which are connected to 2 copies of level n/2 inputs, which are connected to 4 copies of level n/4 inputs, which are connected to n/2 copies of level 2 inputs, which are connected to n/2 copies of level 2 outputs, which are connected to n/4 copies of level 4 outputs, which are connected to 2 copies of level n/2 outputs, which are connected to level n outputs. If one prunes Rn, retaining just the levels starting from level 2 inputs and going thence through the output levels, one has the n-point FFT graph Fn. That is, the graph whose adjacencies reflect the dependency structure of the n-point FFT algorithm. The reader will observe readily that both of our efficient realizations of Rn automatically yield similarly efficient realizations of Fn. The depth-D complete binary tree is the graph whose vertex set is the set of all binary, i.e., 0 to 1, strings of length at most d and whose edges connect all pairs of vertices of the form x and xo, where x is a string and o is a symbol over the alphabet. The W times L planar grid is the graph whose vertex set is the set of pairs W times L and whose edges connect vertices A, B, and C, D just when la CL plus IB DL equals 1. The H times W times L solid grid is the graph whose vertex set is the set of triples H, X, W times L and whose edges connect vertices A, B, C, and D, E, F just. 2 for any integer n denotes the set 1, 2, n. 3-dimensional VLSI. I8. I4. I winky face. I2. R8. 401. I4. I8. F8. Figure 1. The 8 rearrangeable network R8 and the 8-poem FFT graph F8. When AD plus BE plus CF equals 1, we shall view solid grids in two complementary ways. First, we shall view the grids as being composed of faces having dimensions height x width, and second, we shall view the grids as being composed of strata having dimensions length times width. Each stratum of a grid comprises two levels. The purpose of the two levels of a stratum is to allow us to lay wires out on the stratum with crossovers. The crossovers are eliminated by cuts between the two levels of the stratum. We shall never allow more than two wires to cross at a point. When we are discussing one-active level realizations, the bottom stratum plays a materially different role than other strata, since it is where the active devices reside. The purpose of the two levels of the bottom stratum, in this case, is to permit the construction of these devices. Cf. 14, Chapter 1. With this understanding about the use of levels, we shall never have to refer to them explicitly again. Therefore, we shall henceforth refer to strata as atomic objects. Note: we restrict attention in this paper to rectangular, planar, and solid grids for simplicity of exposition. All of the proved and cited results here remain true if we weaken the assumption of rectangularity to convexity. 2.2 Embeddings of graphs in grids. An embedding of the graph GH the grid R, solid or planar, is a one-to-one association of the vertices of G with vertices of I, together with a one-to-one association E of the edges of G with independent paths in 1 inch. When 1 dash is a solid grid, say with dimensions h times w times l, then we say the embedding is a one-active level embedding if all vertices of G are associated with vertices of 1 inch of the form 1 j k. Of course, in place of 1, we could use any flex level IOEH without affecting the results. 2.3 Graph bisectors. Let the graph G have designated disjoint n vertex sets of vertices called inputs and outputs. For m_n/2, an M bisector of G is a set of edges whose removal cuts G into two subgraphs having M and N M inputs, respectively, or having M and N M outputs, respectively. 3. The minimum bisection width of the 3. This noun of input-output bisector is basically the one used M2226. The more commonly used noun of graph bisector, such as S studied in 8, 12, 13, 24, attempts to cut the entire graph G into subgraphs of designated sizes. Both notions are studied M20, and their interrelation is considered. 402. Arnold L. Rosenberg. An vertex graph G is the size of G's smallest /n/2j bisector. Thompson, 22, has shown that a graph's minimum bisection width has great influence on the efficiency with which the graph can be embedded in a planar grid. Not surprisingly, this influence persists in the three-dimensional case, as we shall soon see. 2. For the costs of an embedding. We associate two main costs with an embedding of a graph in either a solid or a planar grid. The first cost is the amount of material consumed by the embedding, measured by area in the two-dimensional and volume in the three-dimensional case. The second cost is the maximum length of any run of wire that does not encounter a device. This length is important since it has a dramatic effect on the speed of a circuit. Depending on the technology in question, this effect is either linear in the length of a run, the transmission line model, or almost quadratic in the length of the run, the diffusion model when discussing on chip timing, 14, page 230. Mead and Conway remark that in MOS technology, the time delay required for a voltage driven onto a wire to equalize across the length of the wire is approximately quadratic with length. The reader is referred to 16 for a discussion of the problems caused by long runs of wires in circuit realizations. In preparation for our study, we now define our two costs formally. The volume, respectively area, of an embedding of the graph G in a solid, ResPec, Tively planar, grid R is the product of the dimensions of 1 dash. The volume, respectively area, of the graph G, VUL, G, respectively area, G, is the minimum volume, respectively area, of any embedding of G in a solid, respectively planar, grid. The one active level volume of the graph G, VOL1, AL, G, is the minimum volume of any one active level embedding of G in a solid grid. The wire length of an embedding of the graph G in a grid is the maximum length of any path E over all edges E of G. The solid, respectively planar, wire length of the graph G, wire, length 3, G, respectively, wire, length 2, G, is the minimum wire length of any embedding of G in a solid, respectively, planar, grid. The 1 active level wire length of the graph G, wire length E, AL, G, is the minimum wire length of any one active level embedding of G in a solid grid. 3. The cost in material. We present the first main result of this paper and contrast it with its two-dimensional counterpart. We begin with the three-dimensional case. Three-dimensional theorem. Let R, N, be the n-rearrangeable network. General embeddings. A VUL, R, N equals ONS/2. B, for any n-permuter G, VUL, G, N3/2. One active level embeddings. C, volley.al, Rn, FFIO, Na/210GN. D, for any n-permuter G with maximum fanout D, volley.al, G equals Na/2 log N, L/2. 4. The general part of the theorem is proved in section 3.1, and the one active level part is proved in section 3.2. The messages of the theorem are A, that n-rearrangeable permutation networks require precisely volume in the neighborhood of Na/2 when realized in a three-dimensional medium, and B, that unrestricted three-dimensional embeddings can be more conservative of material than any one active level 3. For Preparata, 17 has recently exhibited a family, Pn, of n-permuters that have volley-al, Pn equals O Na/2 ln L/2, thus the lower bound of part, D, is odd, and the upper bound of part, E, is not. Three-dimensional VLSI. T / routing. IW. For N/2. EMBOOing. H. Inputs V/I/I. Figure 2. A block diagram indicating schematically how the embedding of Rn is obtained from the embedding of Rn/2. Dimensional embedding. When we consider realizations of Rn in a two-dimensional medium, the exponent increases to 2, two-dimensional theorem. A area Rn equals On2. B for any n permuter G area Gn2. The proof of part A of this theorem is a straightforward modification of the proof of part A of the three-dimensional theorem. The proof of part B of the theorem follows easily from Thompson's 22 method of bounding the area of a graph G in terms of G's minimum bisection width. Details are left to the reader. 3.1 Proof of the three-dimensional theorem for general embeddings. 3.1.1 The upper bound. We shall derive part A of the theorem by describing and analyzing an embedding of the n-rearrangeable network Rn in a solid grid Rn of dimensions On1/2 times On1/2 x On1/2. The vertices of Rn reside in faces of Fn, as indicated in Figure 2. In particular, R2 is embedded in the solid grid P of height 1, width 6, and length 4. The two inputs of R2 reside in the first face of F at positions 3 and 6, and the two outputs reside at the corresponding positions of face 4. Since R is essentially two-dimensional, one can think of faces as columns. The edges of R2 are laid out in R in the obvious way, using faces 2 and 3 for widthwise routing. In order to embed Rn for arbitrary n, let us assume inductively that each Rk less than n is embeddable in a grid Rk in such a way that the input, respectively output, vertices of Rk reside under the embedding in the lowest, respectively highest, index face of Fk at points whose coordinates in the face are of the form 3i, 3j, to embed the non-dash input, output. Vertices of Rn take two copies of Fn/2, each with a copy of Rn/2 embedded in it according to the inductive hypothesis. Lay these copies of the small solid grid together in such a way that their length directions go along the length of Rn, but their height directions go along the width of Rn, and their width directions go along the height of Fn. Make sure, while laying these small grids together, that their input, respectively output, faces are oriented correctly toward the low, respectively high, index faces of Fn, and that their inputs, respectively outputs, are coordinate in the sense that each row of the input faces contains vertices in the format JL n/2, JK n/2, JL n/2, JK n/2. With these small grids as a basis, we now append 2k equals 2/3 h n/2. The value of k derives from our formatting of the vertices of R at positrons of the form 3i, 3j, new faces for edge routing at either end of the adjacent copies of Fn/2, that is, along the length off. Finally, we append one more. For 104, Arnold L. Rosenberg. Face at either end for the inputs and outputs of Rn. These vertices are placed in the appropriate one of the extreme faces at positions corresponding to the vertices of Rn/2 that face it. For example, if the rth row of the input face of the adjacent copies of In/2 has the form JL n/2, JR n/2, phi n/2, J n/2, then row R of the input face of Rn would have the form JL n, JK n, phi plus n slash 2, n, jk plus n slash 2, n. We now describe the embedding of the edges of Rn in In. This description is simplified by two factors, the one being a feature of rearrangeable networks and the other being a feature of the embedding technique just described. First, note that all edges incident to inputs, respectively outputs, of Rn connect these vertices to inputs, respectively outputs, of the two copies of Rn/2. Second, note that in our embedding, these edges always go between vertices that are in the same stratum of Rn. Therefore, we can route these edges within the stratum in the following way. We describe the routing for inputs, that for outputs being analogous. We dedicate one widthwise row of the stratum to each input vertex from the new faces added for wire routing. We then use one lengthwise channel to route an edge between each input of the form j, n, j_n/2 and the opposing vertex of the form j, n/2 and between. Each input of the form j plus n/2, n, and the opposing vertex of the form j, n/2. Finally, we use zigzag length-with-length paths along dedicated channels to complete the required interconnections among these four vertices. Outputs are connected analogously. See Figure 3. Note that our three-dimensional placement of the input and output vertices of Rn permits us to route the level n wires via n1/2 copies of the two-dimensional level n1/2 wire routing. And it is this decomposition that affords us our savings in material and wire length. Since the correctness of the edge layout is obvious, we need verify only that Rn has the right dimensions. This is immediate from the recurrence's height, n equals width n/2 equals 0, nl/2 width n equals 2 height, n/2 equals 0, nl/2 length n equals length n/2 plus 4/3 h, n/2 plus O1 equals 0, nl/2. This verifies part A. 3.1.2 The lower bound. Our proof of part B of the theorem can be viewed as a three-dimensional analog of 22th1, where Thompson bounds the area of a graph G in terms of G's minimum bisection width. Let F be any SOD grid in which any n-permuter P is embedded, and let n be a power of 2, an assumption that simplifies exposition but is easily removed. Say that 1 inch has dimensions h x 4xl where, with no loss of generality, h____4_l, dearly h less than n1/2, or else we are done. Let us pass an hx4 plane along the length of F. There must be a position where the sets A equals the set of outputs of P lying behind the plane in U, B equals the set of outputs of P lying on the plane in R, C equals the set of outputs of P lying before the plane in 1 inch. Satisfy the inequalities 5, n, and 5 we denote by S, the cardinality of the set S. Three-dimensional VLSI. n/2 embedding. Input vertices. 405. Figure 3a top view of the routing of wires, 4-2, butterflies on one stratum of IN. Channels for route, I and G, are delineated by broken lines. Were this not the case, we could derive the contradiction that I contains fewer than n of P's output vertices. Now let us create a unit-length ledge along the height of the bisecting plane whose existence we just established, and let us perturb the position of the distorted plane so that wires pass through it but no vertices of P rest on it. This latter can always be accomplished by placing the plane between integer lattice points rather than on lattice points. One shows easily now that there is some positioning of the ledge that guarantees that at least n/2 and 1/2 of P's output vertices lie behind the distorted plane, and at least a like number reside before the distorted plane. But this distorted plane cuts across wires corresponding to edges of P that constitute an N/2 NA/C bisector of P. We now show that any such bisector must be large. In fact, we establish a stronger result than needed. The graph G is n-reticulated, 8, if vertices G contains two disjoint n-element subsets A and B such that, for all k_n, for all choices of a k-element subset of A and a k-element subset B of B, there exist k-independent paths in G connecting _4 and B. Clearly, any n-permuter is n-reticulated. Lemma. If the graph G is n-reticulated, then for all m_n/2, any m bisector of G has size at least m. Proof. If G is cut so that m inputs reside in one piece of G and m inputs reside in the other piece, then some m outputs of G reside in a different piece of G than some m inputs. By definition of n-reticulation, at least m edges of G must have been cut in order to create this situation. Return to proof of theorem. Our assumption that unit-length wires have unit cross-section, together with the lemma, implies that our distorted plane has area $2, n. Since the plane's actual area is W plus 1, h, this implies that W_cn1/4 some c greater than 0, since W_h, so the same must be true of L_W. It follows that the volume of F is at least dn/2 for some constant d greater than 0. Since the grid R, the permuter P, and the embedding of P and F were arbitrary, it follows that VOL P equals 2n/2 for any n-permuter P. Remark. Our proof of the preceding lower bound is easily seen to prove the more general result. 406. Arnold L. Rosenberg. Theorem 1. There is a constant c greater than 0 such that any graph G with mum bisection with m, hence, in particular, any 2m reticulated graph G satisfies VOL G cm3 halves. 3.2 Proof of the three-dimensional theorem for our one active level embedding of R in R will derive from our unrestricted embed of R in a solid grid, section 3.1.1. By the proof of part A of the theorem, section 3.1.1, there is a constant k such that Rn is embeddable via an unrestricted embedding in a solid grid each of whose dimensions is krn1/2. Each stratum of 1- can be viewed as a 2 krnl/2 ln plus 1 x5 krn1/2. Rectangular grid A comprising 4 regions, as depicted in Figure 4. Region I comprises the first 2 krn1/2 columns of A. These columns will be used for widthwise routing of R's edges. The remaining 3 krn1/2 columns of A are divided into the 3 remaining regions. Region 2 comprises the first krn1/2 rows of M. Region I and Region 3 comprises the last krn1/2 rows of A. Region I. These regions will be used for lengthwise routing of R's edges. Region 4, which consists of the rest of A, will provide a home for R's vertices and will also be used for some wire routing along the channels left free between the vertices of R, cf. section 3.1.1. The vertices of R, i.e., the active devices, will be embedded as follows. Take the embedding of R in a solid grid described in section 3.1.1. Take all the 2 log n faces of that host solid grid that contain images of vertices of R and lay them out in region 4 of the active stratum of I in such a way that each row of one of these faces becomes a row of region 4. Region 4 is thereby automatically subdivided into 2 log n subregions of dimensions kin1/2 x krn1/2, each corresponding to one of the faces used to construct the region. The construction of I is completed by running a vertical metal pole up through all the strata at each position of region 4 of the active stratum that contains a vertex of R. Each pole can be viewed as containing 4 cables, one for each of the edges incident to the vertex from which the pole emanates. The poles will provide the representatives of R's devices/vertices at the corresponding positions of the other strata that are needed to implement R's edges. The cables within the poles make sure that the paths implementing the edges are edge disjoint. Note: we shall treat these poles and the cables they contain informally and not account carefully for the volume they occupy, since we are claiming only a big O result. The reader interested in the actual constants should note that a careful accounting for the poles and cables would increase the volume of I by a factor of roughly 5. We now describe the routing of R's edges in the various strata of I. By the construction in section 3.1.1, every edge of R is accounted for in the following roadmap. Each edge either connects vertices residing in rows R of subregions S and S+1 of region 4, for some odd S and some R K N L/2, or the edge connects vertices residing in column C of subregions S and S+1 of region 4, for some even S and some CE K naught/2. In the former contingency, we route the edges as follows. See Figure 5. Edges that connect corresponding positions of rows are of subregions S. Three-dimensional VLS 1. H. I. 2. I. W. I. 3. 4. 5. Tn. QL. R. G. I. N. Figure 5. A schema-UC view from above of the routing of wires for one butterfly between rows of region 4 of one stratum of our channels are delineated by broken lines. For 107. Figure 4. A schematic view from above of the subdivision of one stratum of F into regions, indicated by Roman numerals, and glons, indicated by Arabic numerals. Subregion I. LIF, IT. FT. I. T. I. I asterisk. IL. 1. R. I. LI dash. I. T. I. Plus or minus. I. 7. IR 7 F it 7. 71 71 IITL SI S plus L S plus 2 and S plus 1 are routed directly between the two regions using the channels that are left free by our sparse placement of R's vertices, edges that connect non-centroresponding. Positions are routed by a widthwise path from subregion S to subregion S1 or 2. Region 2 is equals 1, followed by a lengthwise path to region I, followed by a widthwise path to the latitude of subregion S plus 2, or to region 3 if S is too big, followed by a lengthwise path into this sub-region, followed by a widthwise path to row R of subregion S plus 1. In the latter contingency, the routing is even simpler. See Figure 6. All edges are routed via a lengthwise path from column C of subregion S to region I, followed by a widthwise path through region I, followed by a lengthwise path to column C of subregion S plus 1. In either contingency, the routing honors the following protocols. Recall that vertices of R reside only in rows and columns of the form 3M. 1. For each M, TK, NL/2/3, There is one stratum of P for laying out the edges. Connecting rows 3m of subregions S equals 1, 5, 9, 13, with rows 3m of subregions. Arnold L. Rosenberg. Subregion 1-4, T4. Plus 7-QLQ divided by I plus or minus, H plus or minus, underscore 4 underscore 1 underscore L underscore BLQL. Underscore ZJ underscore forward slash dash 3L. L I 4 T I Lil Li plus 1 dash 1 plus underscore LJ underscore 1 underscore 1 underscore I underscore 1 underscore I T R I L T IF T underscore S plus L S plus 2. Fag 6. A schematic view from above of the routing of WRES41. Butterfly between columns of REM4 of one stratum of F channels are delineated by broken lines. Three-dimensional VLSI. 409. Distorted plane portion of the proof of part B of the theorem, section 3.1.2, we know that HW underscore dn for some constant d greater than 0, letting dh, w, d, we thus have d underscore dn slash d underscore dn slash a slash 2. It follows that volume of if equals HWL equals DDL DNA 1/2 underscore n 3/2 Logan L slash 2. For some constant e greater than 0. The preceding paragraphs exhaust the possibilities and establish the bound. This completes the proof of part D, hence of the theorem. Remark. Our proof of the preceding lower bound is easily seen to prove the more general result. Theorem 2. There is a constant c greater than 0 such that any n-vertex graph G with minimum bisection width m, hence, in particular, any 2m, reticulated graph G satisfies VOL1, AL, G, CMN 1/2. 4. The issue of wire length. The results in the preceding section indicate that there are significant savings in material when n-rearrangeable networks and FFT graphs, and, by inference, similarly densely connected graphs, are realized in a three-dimensional rather than a two-dimensional medium, even when one restricts attention to one active level reahzatlons. However, as we noted in section 2.4, consumption of material is not the only valid measure of the cost of a realization of a graph/circuit. The issue of wire length is a major one. We now show that three-dimensional realizations of graphs/circuits can afford one significant savings in this arena also. We begin our demonstration by continuing with the example of rearrangeable networks and FFT graphs. We shall show that even one active level realizations of these graphs yield wire length costs that are, roughly, the square root of the best attainable two-dimensional wire length cost. There is a sense in which the rearrange able network is a poor graph to use as a model here, since it is a graph which cannot be realized really efficiently, i.e., with ON material, even in a three-dimensional medium. Therefore, we continue looking at this cost measure using the example of complete binary trees. This example demonstrates that even when a graph can be realized efficiently, say with area ON, in a two-dimensional medium, as can binary trees 12, 24. It may be realizable even more efficiently in a three-dimensional medium. The example will also serve to demonstrate that with regard to the wire length cost, unrestricted three-dimensional embeddings may be dramatically more efficient than one-active level embeddings. W&E length theorem 1. Let R, n, be the n-rearrangeable network. Wire length 3 R n equals O n 1/2. And but wire length E underscore AL R n equals O n 1/. Wire length 2 R n equals n/ln. Proof. The three-dimensional upper bounds both follow from the embeddings described in section 3. For instance, an arbitrary wire in the one-active level embedding of section 3.2.1 runs at most ON/2 units along the host solid grid Fs. For 110. ARNOLD L. ROSENBERG RG. Height and length. Since F's height and length are both ONA/2 and at most ON 1/2 units along LS width, since the wire encounters at most 4 subregions of region 4, each having width ON 1/2. The two-dimensional lower bound follows from general considerations based on our lower bound on the total wire length of any two-dimensional embedding of R, n. Specifically, assume that we have established that any type A embedding of R, n, i.e., two-dimensional, three-dimensional, or one-active level, must consume total wire length W, n. It must be then that any type A embedding leads to a wire length cost of W, n, /n ln. This follows since R, n has only O n log n edges. If none of these was represented in the embedding by a wire of length F, W, n, /n, then the total wire length of the embedding would be O, W, n, which is impossible. Our bound on the wire length of two-dimensional embeddings of R, n, now follows from the bound we cited in section 3, in part B, of the two-dimensional theorem. We remarked there that any two-dimensional embedding of R, n has area, n2. In fact, the proof of this bound establishes the stronger fact that any two-dimensional embedding of R, n has total wire length, n2. The theorem follows. For the sake of completeness, we now present lower bounds on the three-dimensional wire LENGTHS of R, n, and note that they are within logarithmic factors of the upper bounds. Proposition. And n 1/2. Wire length 3 R n equals \LGN. n12 wire length L R n equals \, Proof. Since R n has diameter O ln, the claimed bounds are immediate from the following result in conjunction with our lower bounds on the volumes of R n. Theorem 3. There is a constant C greater than 0 such that if G is in degree for n vertex graph with diameter D, then vol G/3 wire length 3G and wire length E.al G C C D max n 1/2 volley.al G 1/3 D. Proof. The three-dimensional analog of an observation by Leighton, 10, th 8, asserts if G is laid out in a solid grid by an A-type embedding E, where A-type is either unrestricted or one-active lever with maximum wire length W, then the volume of that embedding must be bounded as follows. VUL G underscore volume underscore const DW 3. The claimed bound on wire length 3 is now immediate. To complete the proof for wire dash length AL, note that in any one active level embedding of G, some two vertices must be distance at least const nx/2 apart, but in G no two vertices. Three-dimensional VLS. For 111. Are distance more than D apart? It follows that any one active level embedding of G replaces some edge of G by a run of wire in the grid of length at least. Const NL/2/D. We turn now to consider realizations of complete binary trees in grids. The following result illustrates the advantage, relative to the wire length cost of embeddings in grids, of general three-dimensional embeddings as compared with both general two-dimensional embeddings and one active level three-dimensional embeddings. Wire length theorem 2. For any n-node complete binary tree T, n. Wire length ha, T equals 0, NL/3. But, and. Wire length.al, T equals N1/2/ln. Wire length GTH2, T equals NL/2/ln. Proof. We establish the upper bound by presenting an embedding of T equals Tn in a solid grid F of dimensions ON1/XON1/A, XONI/A. The embedding can be viewed as the three-dimensional analog of the well-known extended H construct, tie-in, C, e.g., 14, figure 8.23, used to embed complete binary trees in planar grids in area ON. For simplicity of exposition, we shall assume that the depth of T is a multiple of 3. The reader can easily generalize the construction to arbitrary depths. Assume for the sake of induction that we know how to embed the depth 3D complete binary tree T asterisk, which has n asterisk equals 2 add plus L, 1 nodes, in a solid grid whose height, width, and length are all m, in such a way that the lengthwise channel containing the root of T asterisk contains no other node of T asterisk and contains no wires. 2. Embed the depth 3D plus 1 complete binary tree T, which has n 2a plus 4, 1 nodes. In a solid grid, we take 8 copies of the solid grid that contains T asterisk and place them at the corners of a solid grid whose height, width, and length are all 2m plus 1 in such a way that their heights, widths, and lengths line up with those of the big solid grid. See Figure 7. This gives us an embedding of the bottom of T. To embed the top of T, we place the root of T at the precise center of the host solid grid. We run wires up and down from the root, along the height of the grid, to the centers of the small grids, and we place at those points the sons of the root of T. We run wires from these sons along the width of the solid grid, in both directions, to the centers of the small grids, and we place at the 4 points encountered the grandchildren of the root of T. Finally, we run wires from these grandchildren along the length of the grid into the small grids to connect up with the roots of the copies of T asterisk embedded in the small grids. We are assured of encountering no obstacles, other vertices, or wires on our way to reaching these roots by the inductive assumption of the emptiness of this channel. It should be obvious that our embedding of T is a legitimate one, which preserves the inductive hypothesis. We need, therefore, check only the dimensions of the solid grid holding T. Each of the 3 dimensions clearly satisfies the following recurrence on D, the depth of the tree. D plus I, 2D, D plus I. So that DD equals 2A plus L, 1N1/A. For 112. Arnold L. Rosenberg. Figure 7. A block diagram indicating schematically how the embedding of the depth dash D plus L complete binary tree is obtained from the embedding of the depth D complete binary tree. Since no run of wire in our embedding of T goes farther than DD/4 without encountering a node of T, our bound on wire length 8 is established. Both of the claimed lower bounds follow by the same reasoning as was used at the end of the proof of Theorem 3. Two-dimensional and one active level 3-dimen. Sinal embeddings place T equals Tn S nodes in one plane. So some 2 of these nodes must be placed distance, const, n 1/2 apart, and so the shortest run of wire connecting them must be of similar length. But T has diameter O log n, so some edge of T must be realized by a run of wire of length at least, const, NL/2/ln. The theorem follows. 5. The general layout problem, an application of permuters. There is a precise sense in which permuters are the hardest circuits to lay out. If one can lay out n permuters in volume, respectively area, O, F, n, then one can lay any small degree, say, degree underscore 4, and vertex graph in volume, respectively area, O, F, n. We now verify this claim and note its consequences. A placement of the graph G is a one-to-one mapping of the vertices of G into the set and xn of pairs of positive integers. The dilation of a placement is the maximum, Manhattan, distance in the plane between images of adjacent vertices of G, if vertex V of G gets placed at point H, I, and vertex W gets placed at point J, K, then the distance between their images is IH, Ji plus II, K dot. Thus, dilation is the two-dimensional analog of bandwidth. Idealized and Rosenberg, 1, show that at the cost of a small increase in dilation, say, by a factor of 3, one can restrict attention to placements of G in square regions of side 21G, 1/2, we shall so restrict our attention. 3. Dimensional VLSI. 413. An edge coloring of the graph G is a labeling of the edges of G with colors in such a way that edges incident to the same vertex get distinct labels. A well-known theorem of Ising, 25, asserts. One can always edge color a max degree D graph G using either D or D plus 1 colors. Edge colorings of graphs are important to us here since one easily verifies that for any color R, the transformation of vertices, G, def med by vertex U gets mapped to vertex V just when U and V are connected by a color R edge, and is fixed otherwise, is a permutation of vertices, G. We can combine Ising's theorem, the preceding observation, and our efficient three-dimensional realization of the n-rearrangeable permutation networks to prove the following. General layout theorem. If the max degree, 4, and vertex graph G admits a dilation, 6n, placement, then there is an embedding of G in an ON 1/2 times ONL/Z XO6n three-dimensional grid so that VUL G equals ONSN and wire length 3 G O8 N. In particular, since 6n equals ON 1/2 for every n vertex graph, every max degree for n vertex graph G has VUL G equals ON/2 and wire len GTH3 G equals ONX/2. Proof. We shall only sketch the necessary construction, relying on the reader's familiarity with sections 3.1.1 and 3.2.1 to flesh out the sketch. We begin by laying the graph G out in the plane using a dilation, 8, n, placement. As we noted before, we risk only a small constant factor's inefficiency by insisting that the placement be in a square region of side ON 1/2. For each of the at most 5 colors used to edge color G, we tile the square region with a 3-layer brick wall whose bricks are 26 n, x26 n, x28 n, 462 n, permuters as follows. The first layer of permuters is used to tile the square region completely so that every vertex of G has above it 1 input and 1 output, vertex of one of the tiling permuters. We use smaller permuters near the boundaries of the region if necessary. The second and third layers of permuters tile the region in a similar fashion, but the second layer is offset by d, n along one dimension, and the third layer is offset by 6, n along the other dimension. Just as bricks are offset in a wall, now we augment the layout so that each vertex of G has a pole containing 4 cables, one for each edge incident to the vertex, stretching up through the, at most 15, layers of permuters above that vertex. These cables serve the same role here as they did in the one active layer construction of section 3.2.1. By dint of the arrangement of the cables and the permuters, each vertex of G has the potential to be connected, via the cables and its pole, to any four of the permuter inputs and outputs that lie above it. 414. Arnold L. Rosenberg. To illustrate how the edges of G are connected up using the banks of permuters, let us concentrate on the realization of a single red edge, U, V of G. Because of our arrangement of the red permuters, and because of G's dilation, there is some red permuter that has an input vertex lying above vertex U of G and an output vertex above vertex V of G. We use one cable from U's pole to connect U to that input vertex, and we use one cable from V's pole to connect V to that output vertex. Once we have established all the input-output connections for the red edges, we can set the switches of the red permuters to realize the permutation of G's vertices affected by the red edges. For reasons of speed and compactness, once the permuters are set, they should be permanently set and pruned in that configuration. Reconfigurability is not our goal here. The effectiveness of our layout strategy should be clear. The dimensions of the layout are length and width ONL/Z each, to accommodate the placement of G's vertices and their poles, and height O6N, to accommodate up to 15 permuters of dimensions O8N times O8N times O6N each. The details necessary to complete the proof are straightforward and are left to the reader. The use of permuters as conduits for the edges of graphs has its origins in the work of Hoffman, 15, and Valiant, 23. The major difference between our use of permuters and theirs is that we prune our permuters in order to realize a particular edge association, while they, in their quests for universality, i.e., reconfigurability, retain the settability of the permuter switches. Remark. By combining the construction of the general layout theorem with Preparata's improvement on our construction in section 3.2.1, one can show that any small degree and vertex graph G has vol1.ALGON3/21 It is well known that there are small degree and vertex graphs G with f, n, minimum bisection widths. For example, there are f, n, retilated and vertex graphs. One proves easily by the techniques of section 3.1.2 that such graphs have VUL, G equals n3 halves, and wire, length 3, G equals n1/2, thus, at least in extreme cases. The construction of the general layout theorem cannot be improved by more than a constant factor. 6. Concluding remarks. We have demonstrated dramatic efficiencies in three-dimensional circuit realizations that are not attainable in 2 dimensions. Moreover, the benefits of these efficiencies in orders of growth are not delayed by huge constants hidden in the big O(s). The reader can determine easily that the constants in our constructions are very small. The reader familiar with papers such as 1722 will note that techniques for bounding the volumes and areas of layouts of circuits can be adapted easily to techniques for comparing the efficiency measures area, time 2, and volume, time A/2 for functions. This topic merits further attention. There are many issues concerning circuit layouts that also demand further study. The efficiencies we have observed in three-dimensional layouts are of sufficient magnitude that further research is warranted on 2 question areas. First, how widespread are the advantages of 3 dimensions over 2? Because of recent joint work with latent 11, we know that the results reported here extend to large families of graphs, graphs with ON, separators, a recursive generalization of bisector, all have volume roughly ONZ/2, while some of these graphs have 415 area and 2 foot. But we do not yet know how common such savings are in real circuits. Moreover, we have yet to look at the impact of the availability of the third dimension on such areas as wire routing. And what effect will the availability of the third dimension have on the inefficiencies of array logic? Second, are the technological impediments to three-dimensional circuitry likely to be surmounted in the foreseeable future, or are they so tied to the current state of the technology that only a revolutionary advance will overcome them? We have some encouraging evidence regarding this topic, 3 to 7, 21, 27, but we have yet to see in print any definitive evidence of either possibility. Acknowledgement. It is a pleasure to thank Larry Stockmar for several valuable suggestions and for a careful reading of an early version of the TypeScript. References 1. ALLRNS, R, and Rosenberg, AL. On embedding rectangular grids in square grids. IEEE Transcomput. C31, 9, September 1982, 907 to 913 2. BNRS, VE, Optimal Rearrangeable Multistage Connecting Networks. VLSI, Tech J, 43, 1964, 1641 to 1656. 3. ETCMD, LLS, RDD, Cummings, AD, Grinberg, J, and NUD-GR, Cellular Array Architecture for Microelectronic Implementation. In Preparon. 4. ETC Char LLS, RDD, Cummings, AD, Grinberg, J, and NUD-GR, a yield redundancy policy for wafer scale integration. In Preparon. 5. Echels, RD, Cummings, AD, Grinberg, J, and NUD-GR, Power Dissipation in 3D VLSI. In Preparon. 6. Echels, RD, Grin G, J, and NUD-GR, Development of a Three-Dimensional Circuit Integration Technology and Computer Architecture Unpushed Manuscript, 1981. 7. Gibbons J.F., SOA Candidate for VLSI? VLSI Design 3, 1982, 54 to 55. 8. Hong, J, *W, and Rosenberg, AL Graphs that are almost binary trees. Siam J, Comput. 11, 1982, 227 to 242. 9. LM, HW, TSCN, A.F, JR, and Holloway, TC Characteristics of MOSFETs, Fabricated and Laser Recrystallized Polysilicon Islands with a retaining wall structure on an insulating substrate. IEEE Electron Dev, Let EDL, 1, 1980, 206 to 208 10 Layton, EFT, T New Lower Bound Techniques for VLSL Intel and FREC, 22 RID, and IEEE Syrup. On Foundations of Computer Science, Nashville, Term, 1981, IEEE, New York, 1981, pages 1 to 12. III, Layton, FT, and Rosenberg, AL. 3-Dunans onal ORCID layouts. In Preparation. 12. Liserson, C. Area Efficient VLSI Computation. Ph.D. Dissertation, Carnegie Mellon University, Pittsburgh, Pennsylvania, 1981. See also, Area Efficient Graph Layouts, for VLSI. In Prec 21st IEEE Syrup. On Foundations of Computer Science, Syracuse, New York, October 1980, IEEE, New York, 1980, pp 270 to -281. 13. Lipton, R.J., and Tiatun, R.E. A Separator Theorem for Planar Graphs. SII ZAPPL, Math. 36, 1979, 177 to 189. 14. Mead, C. and Conway, L. Introduction to VLSI Systems Addison Wesley, Reading, Mass., 1980-15. Offman, U.PA Universal Automaton. Trans Moscow Math. SOC 14, 1965, 200 to 215. 16. Patterson, M.S., Rutso, WL and Snyder, L bounds on minimax edge length for complete binary trees. In Prec 13th ACM Syrup on Theory of Computing, Milwaukee, Wise, 198-0, ACM, New York, 1981, pp 293-299. 17. Preparata, F. Optimal three-dimensional VLSI layouts. Math SYSD, Theory 16, 1983, 1-8, 18 Rosen, D. TCMets, a new word for density M logic packaging think. Jams/February 1981, 23. 19 Rosenberg, A.L. Three-dimensional integrated circumtree. In VLSI systems and computations, H.T. Kung, R. Sproul, and G. Steele, eds. Computer Science Press, Rockvaiui, M.D., 1981, pages 69-80. 20. Rosenberg, A.L. Graph separators. In Preparon. 21. Soskind, G. Private Communication, 1982. 22. Thompson, CD Area Time Complexity for VLSI and Proc LLTH ACM Syrup. On Theory of Computing, Atlanta, Georgia, May 1979, ACM, New York, 1979, pp 81-88 23 Valiant, L. G. Versal Circuits in Prec 8th ACM Syrup on Theory of Computing, Hershey, Pennsylvania, May 1976, ACM, New York, 1976, pp 196-203 24. Valiant, L. G. Versati Considerations in VLSI Orchid's IEEE Trans Compu C. 30, 1981, 135-140. 416. Arnold L. Rosenberg. 25. Vising VG. On an estimate of the chromatic class of AP graph. Discret. Analyze. 3, 1964, 25-30 in Russian. 26. VTNI.Lemon, J. A combinatorial limit to the computing power of VLSI circuits. In CONF Rec. 21st N. IEEE Syrup. On Foundations of Computer Science, Syracuse, New York, October 1980, IEEE, New York, 1980, pages 294-300. 27. YNI-RG, ZA polysilicon recrystallization by CO2 laser heating of CO. Tech Representative RC, 8835, IBM Thomas J. Watson Research Laboratory, Yorktown Heights, NY, 1981. Received March 1981. Revised December 1981. Accepted June 1982. Journal of the Association for Computing Machinery, Volume 30, Number 3, July 1983.